Chapter 12.1, Sampling, Frequency Distributions, and Graphs. Okay, and this is our last chapter, so hopefully everyone is doing well, going towards the end, ready to finish up on a nice note. Let's look at what we have. The word statistics is often used when referring to data. However, statistics has a second meaning. Statistics is also a method for collecting, organizing, analyzing, and interpreting data, as well as drawing conclusions based on the data. This methodology divides statistics into two main areas. Descriptive statistics is concerned with collecting, organizing, summarizing, and presenting data. Inferential statistics has to do with making generalizations about and drawing conclusions from the data. Some terms we need to know. A population is the set containing all the people or objects whose properties are to be described and analyzed. A sample is a subset or subgroup of the population. So, for example, if we had a group of hotel owners in a large city that decide to conduct a survey among citizens of the city to discover their opinions about casino gambling, and were asked to describe the population, that would be the entire population of the city. The sample would be the actual people that were questioned or given the survey. Now, one of the hotel owners suggests obtaining a sample by surveying all the people at the 6 largest nightclubs in the city on a Saturday night. Okay, each person will be asked to express his or her opinion on casino gambling. Does this seem like a good idea? Surveying people at 6 of the city's largest nightclubs does not seem like a good idea. Let's consider the sampling fiasco that happened in 1936. The Literary Digest mailed out over 10 million ballots to voters throughout the country. The results poured in, and the magazine predicted a landslide victory for Republican Alf Landon over Democrat Franklin Roosevelt. All right, let me ask you, have you ever heard of President Alf Landon? No. The prediction of the Literary Digest was wrong. Why? The mailing list the editors used included people from their own subscriber list, directories of automobile owners, and telephone books. As a result, its sample was anything but random. It excluded most of the poor, who were unlikely to subscribe to the Literary Digest, or any magazine, or to own a car or telephone in the heart of the Depression. Prosperous people in 1936 were more likely to be Republican than the poor. Thus, although the sample was massive, it included a higher percentage of affluent individuals than the population as a whole did. A victim of both the Depression and the 1936 sampling fiasco, the Literary Digest folded in 1937. Now, there is a way to use a small sample to make generalizations about a large population. Guarantee that every member of the population has an equal chance to be selected for the sample. And as we were talking about the question about the casino, unless it can be established that all citizens of the city frequent these clubs, which seems unlikely, this sampling scheme does not permit each citizen an equal chance of selection. A random sample is a sample obtained in such a way that every element of the population has an equal chance of being selected for the sample. In random sampling, each element in the population must be identified and assigned a number. The numbers are generally assigned in order. The way to sample from the larger numbered population is to generate random numbers using a computer or calculator. Each numbered element from the population that corresponds to one of the generated random numbers is selected for the sample. Another example of that is put all the numbers in a hat. All right, stick your hand in, shake them around, draw one out. That's random. As long as there is a paper in the hat that represents every member of the population. Call-in polls on radio and television are not reliable because those polled do not represent the larger population. A person who calls in is likely to have feelings about an issue that are consistent with the politics of the show's host. For a poll to be accurate, the sample must be chosen randomly from the larger population. Surveys and polls involve data from a sample of some population. Regardless of the sampling technique used, the sample should exhibit characteristics typical of those possessed by the target population. This type of sample is called a representative sample. Okay, so after data have been collected from a sample of the population, the next task facing the statistician is to present the data in a condensed and manageable form. In this way, the data can be more easily interpreted. Suppose, for example, that researchers are interested in determining the age at which adolescent males show the greatest rate of physical growth. A random sample of 35 10-year-old boys is measured for height and then remeasured each year until they reach 18. The age of maximum yearly growth for each subject is as follows. Okay, so in other words, this 12-year-old had his maximum growth when he was 12. This boy had his maximum yearly growth when he was 14, etc. A piece of data is called a data item. This list of data has 35 data items. Some of the data items are identical. Two of the data items are 11 and 11. Okay, thus we can say the data value 11 occurs twice. Similarly, because let's see, we have 1, 2, 3, 4, 5 of the data items that are 12, the data value 12 occurs 5 times. Collected data can be presented using a frequency distribution. Such a distribution consists of 2 columns. The data values are listed in one column. Numerical data are generally listed from smallest to largest, and then the adjacent column is labeled frequency and indicates the number of times each value occurs. Since it's difficult to determine trends in the above data, perhaps we can make sense of the data by organizing them into a frequency distribution. So my first step, I notice I'm on red, but that's okay, I guess. We're normally blue, but I don't think that's a big deal. My first step is to make a table with 2 columns. Okay. And so my first column, I'm going to label age. And this one is always frequency. Always frequency. And then I look at my data and I see that I've got a 10. That's my smallest data. Here's an 18. Is there anything larger than an 18? No. So I'm going to need rows that go from 10 to 18. 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. And that goes in the left-hand column. And then my last one is the total. And this total right here better be 35, right? Because it tells me there's 35 boys in this sample. So here's a double check for me. These better add up to 35. Now, 10. I'm going to see how many boys were 10 when they had their biggest growth spurt. Just one. How about 11? 1, 2 boys were 11. And I'm going to do the same all the way across. 1, 2, 3, 4, 5. Yeah, we counted the 12s just a minute ago, didn't we? 13. 1, 2, 3, 4, 5, 6, 7. Okay, 14 is 1, 2, 3, 4, 5, 6, 7, 8, 9. 15, 1, 2, 3, 4, 5, 6, 16, 1, 2, 3, 17, 1, and 18 looks like 1. Keep some way to keep track to make sure you've accounted for all of the data items, and as a double check we can add these up. Here's 10, 15, 24, 33, 34, 35. Check. So this is a frequency distribution table. Okay, it indicates that one subject had maximum growth at age 10, 2 at age 11, 5 at age 7, 7 boys had their maximum growth at age 13, and so on. We can see that the maximum growth for most of the subjects occurred between 13 to 15, right? And 9 boys experienced maximum growth at age 14. In other words, the biggest amount, more than any other age within the sample, experienced maximum growth when they were 14. And we can see that the trend indicates that the number of boys who attained their maximum growth at a given age increases until 14 and then decreases after that. Lots of things we can determine from the frequency distribution that we could not tell just from the list of data. Okay, let's look at that some more. A frequency distribution that lists all possible data items can be quite cumbersome when there are many such items. Okay, look at this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I would need my frequency distribution to have 40 rows if we continued to do it the way we did the last one. So one way to organize these data so that the results are more meaningful is to arrange the data into groups or classes. The method for organizing data, this method for organizing data is called a grouped frequency distribution. The leftmost number in each class is called the lower class limit. The rightmost number in each class is called the upper class limit. If we take the difference between any two consecutive lower class limits, we should get the same number. This is called the class width. When setting up class limits, each class, with the possible exception of the first or last, should have the same width. Let me give you a quick example of why we allow this exception of the first or last. Let's say an easy thing to think of where you would do a grouped frequency distribution is perhaps grades. And actually that's what we've got here, class scores for a group of 40 students. And we could group them into A's, B's, C's, D's, and F's, right? Well, think about what that means. Yes, the D is 60 to 69, the C 70 to 79, the B 80 to 89, but think about an A. It's 90 to 100, not just 90 to 99. It has that extra point in there. And an F is everything below a 60, so 0 to 59. So we are allowed, just by the nature of some kinds of data sometimes, to have the first and or last class a different width. But other than that, right, all the classes must have the same width. So let's make a grouped frequency distribution to organize this data. Again, it's 2 columns. And the second one is always your frequency. And on this one, we'll say grades. Okay. So if we are going to organize these, let me look over here and see what my lowest score is here. I've got something in the 40s. Here's some more 40s. Okay, so I can either group them from 40 to 49 and up, or like I said, we can just count the 40s and 50s all as basically an F. So whichever way you prefer, or pay attention on your homework to see if it gives you detailed instructions. So let's just do, since it only goes to 40, we can do an extra 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89, and 90. Now, I'd look over here quickly, and I see I don't have a 100, so I couldn't do 90 to 99, but I'm going to do 90 to 100, since I know it's very possible to have a grade of a 100. And then finally, I'm going to have a total. And as a double check, that total better be 40, because I've already counted up 8 by 5. I have 40 scores. So 40 to 49, how many fall in this 40 to 49 group? 1, 2, 3. 3 grades in the 40s. 50s, 1, 2, 3, 4, 5, 6. Now I'm looking for 60s. 1, 2, 3, 4. 70s, I've got 1, 2, 3, 4. Oh, I missed a 60. Look, so a 60, I need to change that to 5. So really find some way to organize your data. I'm going to go back with 70s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the 80s. 1, 2, 3, 4, 5, 6, 7, 8, 9, and the 90s. 1, I missed another 60. 2, 3, 4, 5. Okay, so I need to add 1 to this 60, making that 6. So this is also an excellent example of why I'm going to double check it with my 40 down here. What if, as I added those 60s and I already had some of my 70s marked out, I missed a 70 that was already marked out. But here's a check for me. Okay, here's 25, right? 35, 37, 38, 39, 40. Perfect. Add them up and they've got to be 40. Now, notice that my class widths are 10. Don't say they're width of 9. A lot of people mistakenly think, oh, 40 to 49. But the way I can find my class width is subtract either your lower or upper class limit from the one before. 60 minus 50 is 10. Think about this. If you count from 40 to 49, you're getting 40 is actually your first data value. So that 0 counts as 1. So 40, 41, 42, 43, 44, 45, 46, 47, 48, 49. That's 10. Okay, so be careful about what you answer your class width as being. And all I need to do is pick a couple of groups in the middle and subtract either the lower limit from the lower limit or upper from the upper, but do not subtract the upper and lower in the same class. Hopefully that makes sense. Okay, so frequency distribution tables and grouped frequency distribution tables. All right, let's take a look at the second let's take a second look at the frequency distribution for the age of a boy's maximum yearly growth. And I've recreated it down here already so that we can refer to it. A bar graph with bars that touch, that's important, the bars must touch, can be used to visually display the data. Such a graph is called a histogram. On a histogram, the bars must touch. On a bar graph, the bars do not touch. Okay, a series of rectangles whose heights represent the frequencies are placed next to each other. So notice the height of the bar for the data value 10 is at 1, indicating there was one boy age 10 who had his maximum growth. Let's look at 12. The height of the bar for the data value 12 is at 5. Right? Your frequency is always on your vertical axis. Right? This is the number of boys with maximum yearly growth. Their frequency, the number of them. And here's the age in years, or your data values. Okay, the break along the horizontal axis right here, this little zigzag, symbolize that there's some missing data value. So that's how we get away with just starting at 10. We say a break here and say, oh, well, okay, we're missing the data values from 1 through 9. A line graph, called a frequency polygon, can also be used to visually display the information shown in a histogram. So once a histogram has been created, it's very easy to draw a frequency polygon. You simply put a dot. If you already have your histogram drawn, then a dot in the middle of each bar. But technically, I mean, we won't really have them on the same plot, but instead of drawing the bars, everything is set up the same way. This is your frequency, here's your data, and you'll put a dot at the heights, same distance apart, and connect them with straight lines. Connect the dots with straight lines. Imagine that they're straight, right? Use your imagination. All right, and then finally, a histogram will connect at the front and end to the bottom. So here it is, and this is after I took off the bars to show simply the frequency polygon, and it kind of got rid of my axes across there, but I think that's okay. So a histogram looks like this. The frequency polygon is drawn in red, or the frequency polygon alone, and a frequency distribution. We have one more kind of chart to talk about, so let's go ahead and look at that. A stem and leaf plot. Okay, the plot is constructed by separating each data item into two parts. Okay, the first part is the stem, and the second part is the leaf. So I'm going to make like a T chart here, and I'm going to have stems and leaves. Now, it's really important, your book doesn't really go into this much detail, but it's really important on a stem and leaf to have a key somewhere. So I'm going to have a key down here that says how to interpret my graph. Because my data points could have been 8.2, 4.7, 7.5. I could have let my stem be the whole number and the leaves the decimals. Or if these were in the hundreds, I could let my stem be the hundreds. If this was 825, my stem could be 8 and my leaf could have been 25. Right? 472, stem 4, leaf 72. So I need some kind of interpretation of how to read this stem and leaf. All right, so my stems, let's see, they go from 4 through 9. And it's really easy. I'm just going to go through 82. Will look like this, right? 47, 75, 64, 57, 82, 63, 93, 76, 68, 84, 54, 88, 77, 79, 80, 94, 92, 94, 80, 94, 66, 81, 67, 75, 73, 66, 87, 76, 45, 43, 56, 57, 74, 50, 78, 71, 84, 59, and 76. Whoops, 76. Okay, and it's just another way to organize your data. Now, look at this. If I were to turn this sideways, I get the same shape as a histogram. Whoop, sorry. Looks. So imagine turning that sideways, and I have that histogram view of it. And just like a histogram or a frequency distribution or a frequency polygon, I have a lot of things I can tell about this that I cannot tell from a simple list of data over here. I can tell just at a glance that most scores were in the 70s, right? And I can tell exactly how many. I can tell that the vast majority of students made 70s and 80s, right? My lowest score was a 43, the highest score was a 94. An advantage over the histogram is that the stem and leaf plot preserves exact data items. So not only can I see that most scores were in the 70s, I could look at the exact values and say, well, were they in the low 70s or high 70s? And I noticed that mostly the high 70s. I had a 73 and a 71, and a 74, but then my others were 75, 6, 7, 79, 76, 78, 76. So mid to upper 70s. I do not lose my exact data items. However, the advantage of the histogram over the stem and leaf is, what if I had 400 data items? I would have to write each value of the 400 values instead of just grouping it into a bar. So both of them have advantages and disadvantages. And we'll continue to look at these as we go along. Okay. Benjamin Disraeli, Queen Victoria's Prime Minister, stated that there are lies, damned lies, and statistics. The problem is not that statistics lie, but rather that liars use statistics. Graphs can be used to distort the underlying data, making it difficult for the viewer to learn the truth. One potential source of misunderstanding is the scale on the vertical axis. That's the first thing you should always look at. Okay, the scale is important because it lets a researcher inflate or deflate a trend. For example, both of these graphs present identical data for the percentage of people in the United States living below the poverty level from 2001 through 2005. Here's the actual data values. Right? The graph on the left stretches the scale on the vertical axis to create an overall impression of a poverty rate increasing rapidly over time. The graph on the right compresses the scale on the vertical axis to create an impression of a poverty rate that's just slowly increasing and beginning to level off. Okay, so always look at your vertical axis and see, are they zoomed in or zoomed out, right, to make their point. Another problem with this data might be that depending on the time frame chosen, you could interpret it in various ways. Look, it only goes from 2000 to 2004. Why aren't we going up to 2015? Or what happened from 1990 to 2000? So since it's just a small time frame taken, it could have been selected to put either the most positive or most negative light, whatever point you were trying to prove. So, things to watch for in visual displays of data. Is there a title that explains what is being displayed? You must have a title on your charts or graphs. Are numbers lined up with tick marks on the vertical axis that clearly indicate the scale? Right, so make sure that the scale is indicating. Has the scale been varied to create a more or less dramatic impression than shown by the actual data, like the example we just looked at? Do too many design and cosmetic effects draw attention from or distort the data, like we're going to look at down here? And now that we have computers to make these graphs, people tend to overuse these three-dimensional and fancy effects, and it makes it really easy to distort the data. Has the wrong impression been created about how the data are changing because equally spaced time intervals are not used on the horizontal axis? So another thing to look at along with the vertical axis is your horizontal axis. Furthermore, has a time interval been chosen that allows the data to be interpreted in various ways, like we mentioned previously? Are bar sizes scaled proportionately in terms of the data they represent? Is there a source that indicates where the data in the display came from? Okay, always check your source. Back in the 70s, the tobacco companies had data that they were presenting that said cigarette smoking was not harmful to your health. Okay, always check the source. Do the data come from an entire population or a sample? Was a random sample used? And if so, are there possible differences between what is displayed in the graph and what is occurring in the entire population? Who is presenting the visual display, and does that person have a special case to make for or against the trend shown by the graph? So for example, here's a display of the number of square feet in an average U.S. single-family home. Okay? Cosmetic effects of homes with equal heights, so the homes all have equal heights, but different frontal additions and shadow lengths make it impossible to tell if they proportionately depict the given areas. Time intervals on the horizontal axis are not uniform in size, 10 years here and then a gap of 20 years, making it appear that dwelling swelling has been linear from 1980 through 2010. The data indicate that this is not the case. There was a greater increase in area from 1980 through 1990. Look at this, 1740 to 2080 square feet, averaging 34 square feet per year. But from 1990 through 2010, it only averaged 15.6 square feet per year. So look at all of these kind of things anytime you are given some information represented pictorially in a graph or chart or some kind of display. Very easy to mislead. All right, let's look at some questions and see what we can do here. The city council of a large city needs to know whether its residents will support the building of 3 new schools. The council decides to conduct a survey of a sample of the city's residents. Which procedure would be most appropriate for obtaining a sample of the city's residents? A. Survey a random sample of teachers who live in the city. Let's just debunk them or give them credit as we go along. Do you think that would be an appropriate sample, a random sample of teachers? No, of course not. Right? Even though it's a random sample, if you only sample teachers, that's not representative of what the entire city may feel. Of course, teachers probably want a new school, job security, right? B. Survey 100 individuals who are randomly selected from a list of all people living in the state in which the city in question is located. What about this one? Would that be a good sample? No. Again, even though they're randomly selected, the people living in the state are not from the population, right? People in the city. Survey a random sample of persons within each neighborhood of the city. There, that sounds like a great idea, right? Each neighborhood, so everyone in the entire city has an equal chance of being selected since they're going to choose people from each neighborhood, not only the affluent neighborhoods or the neighborhoods along the river or whatever, every neighborhood, and it's random. Survey every 10th person who enters City Hall on a randomly selected day. What's the problem with that one? Not every person has an equal chance to be selected. Only the people who go to City Hall. When's the last time any of you guys have been to City Hall? Okay, so C. A college professor had students keep a diary of their social interactions for a week. Excluding family and work situations, the number of social interactions of 10 minutes or longer over the week is shown in the group frequency distribution at the right. Okay, so let's figure out what this is to start with. The number of social interactions of 10 minutes or longer, right? So the people that had from 0 to 4, either 1, 2, or 3, social interactions during a week, there were 12 people that had 0 through 4, 10-minute or longer social interactions, right? 3 people had from 45 to 49, 10-minute or longer social interactions. Okay. Identify the lower class limit for each class. 0, 5, 10, 15, 20, 25, 30, 35, 40, and 45 are the lower class limits. The upper class limits are 4, 9, 14, 19, 24, 29, 34, 39, 44, and 49. What is the class width? 10 minus 5 is 5, right? Don't do 9 minus 5 or 14 minus 10. The class width is 5. Think about this. Let's count these on your fingers. 0, 1, 2, 3, 4. The class width is 5. How many students were involved in this study? Well, we can add them up right here. 10, 20, 30, 40. You can plug it on your calculator, whatever. 10, 20, 30, 40, 50, 60, 72, 81, 85, 86, 7, 88. I got 94, adding them up in my head. But that's what we want to do. You know, may or may not have been 94. I did it in my head. Plug it on your calculator. However, just add all of these up. And that's the number of students involved in this study. How many students had at least 30 social interactions for the week? At least 30 means 30 or more, right? Well, then that's this group right here, right? 30 or more. So 4, 7, 10, 13 students had 30 or more. Among the classes with the greatest frequency, which class had the least number of social interactions? So among the classes with the greatest frequency, here's the greatest frequency. Which class had the least number of social interactions? 5 to 9. Okay. As of 2011, the following are the ages in chronological order at which U.S. presidents were inaugurated. So here's my data. Construct a group frequency distribution for the data. Oh, and it gets me started. Use 41 through 45 for the first class, and of course the same width for each subsequent class. So if I'm making a group frequency distribution, okay, and frequency is always the second column. This would be ages. And I've got to start with 41 through 45. And I probably want to see what my oldest person is. There's a 69. Okay, 69. So 41 through 45, 46 through 50, make them the same width. So this next one should start with 51 through 55, right? 1 through 55. 56 through 60. 61 through 65. 66 through 70. And let's have a total on the bottom to double check ourselves. All right, let's count from 41 through 45. One, two. 46 through 50. 1, 2, 3, 4, 5, 6, 7, 8, 9, 51 through 55. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 56 through 60. 1, 2, 3, 4, 5, 6, 7, 8, 9, 61 through 65. 1, 2, 3, 4, 5, 6, 7, 66 through 70. 1, 2. All right, let's add these up. 18, 19, 20, 35, 44. And let's make sure that's 44 data items. Make sure I accounted for them all. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 1, 2, 3, 4. Good. I've got everything accounted for. How many presidents were inaugurated? Well, we just found that out. 44, right? So right here is my total. How many presidents were inaugurated while in their 60s? Okay, in their 60s, 9. That's really kind of a bad question. Instead of in their 60s, it should say were inaugurated while over 60, right? Because I've got some in here that 60s. I'd have to go back and see how many are 60s. So bad question there that I came up with that. Sorry about that. Okay, so we're going to say 9. How many were inaugurated while younger than 45? Right? 2. And again, this should say 45 or younger, because younger than 45 implies, so it needs a little bit of correction on this. Let's make this 45 or younger. Okay, that's a better question. Okay, so my frequency distribution table, and again, once I get my frequency distribution table completed, I can answer all kinds of questions about it. My data is organized. I can see that by far most presidents run from 51 through 55. It's very unusual to have a president, or has been unusual to have a president below 45 or over 65. Now it's asking me to construct a frequency polygon, a histogram, a frequency polygon, and a stem and leaf. So for a histogram, to construct a histogram, and remember, always label. So we're going to put our frequency here. If I can write sideways on this. My arm to use this thing is already has to be a little bit Oh, lopsided, and so do I sideways when I'm already lopsided. It's really crazy. Okay. Ages. Now, I can look, after I've got my data organized in a frequency distribution, if I were just asked straight to construct a histogram without going through the frequency distribution, this is still going to be the first step I do. I'm still going to go over to the side and make a frequency distribution. Okay, and then that tells me what my bars are. So, oh, again, I don't know if I can write sideways. So 41 to 45. Oh, this is going to be so bad. Okay, so I'm going to have a bar width here. I'm going to make my little jag. Okay, 46 to 50, 51 to 55. I cannot write sideways on this thing. 56 to 60, 61 to 65, and 66 to 70. And then my frequency needs to go up to 15. So I might go by twos. 2, 4, 6, 8, 10, 12, 14. Okay, 2, 4, 6, 8, 10, 12, 14. So make sure everything's nicely labeled and numbered. And then 41 to 45, I'm just going to draw a bar that goes up to the 2. Again, my bars must touch and they must be the same width. So now I need to go up to 9, make it the same width, and then up to 15, same width, and then I've got another one at 9, the same width. Sorry, imagine I can draw straight. And then one at 7, the same width, and then back to 2. A little bit off on my 2 there. The same width. Okay, so for my frequency polygon, we're just going to imagine, because this was really difficult for me to do sideways, so I'm going to, this blue part is going to stay the same. The only difference will be, instead of a bar that goes that high, I will put a dot at the center. Right? And then draw a straight line. Imagine that I can draw a straight line between the dots. Can actually connect the dots, okay? And end it by connecting it to the horizontal axis. Okay, so your frequency polygon should look like this. And then finally, a stem and leaf. So for a stem and leaf, I need my stem and my leaves. And I need a key somewhere. So my key, I'm going to say 5/7 equals 57. And then I'm just going to go back up to the data, right? And I know I'm going from 4s through 6 for my stems. 4, 5, 6. So 57, 61, 57, 57, 58, 57, 61, 54, 68, 51, 49, 64, 50, 48, 65, 52, 56, 46, 54, 49, 50, 47, 55, 55, 54, 42, 51, 56, 55, I hope I don't run off the page, 51, 54, 51, 60, 62, 43, 55, 56, 61, 52, 69, 64, 46, 54, and 47. And I have a stem and leaf. Okay. Please let me know if you have any questions, and we will pick up next time.